it's time for our first keynote. It's given by Steve Vogelsang, the CTO of Nokia Federal Solutions. Unfortunately, something came up and he had to cancel the trip in the last minute, so it will be a video. But we will have many Nokia colleagues who kindly volunteered to answer any questions you might have. So I think that's a brave take, so I appreciate that a lot. So let's have the keynote and then there will be chance for questions.
Good morning. My name is Steve Vogelsang, and I'm the Chief Technology Officer for Nokia Federal Solutions. Very happy to be here today virtually. I was looking forward to visiting Oulu, but unfortunately, last minute critical item came up for this week, and I was not able to make the trip. But I'm happy that I can at least be here virtually and provide this keynote presentation to y'all. A little bit on my background and what I do will give some context for the presentation. As the CTO of Nokia Federal Solutions, I look after the technical team for a subsidiary of Nokia, NFS, which focuses on working with the US government. So we help the US government figure out how to leverage Nokia's products and technology for various missions. And a lot of that work is done with the DoD and focused on defense networks. So what I'll talk about today is really looking at how are cellular technologies being applied for defense purposes, and then really looking at where and how we see 6G coming into the equation, and what are some of the key capabilities from at least my perspective that are coming in 6G, and how do we see them impacting defense networks. So let me start by giving some background on where and how cellular network is currently being used and how the Department of War is being organized. So first question is, well, why? Why cellular networks for defense? It's a fair question. There are a lot of different tactical radio technologies that have been around for quite a long time. There's continuous innovation in the defense industrial base to create new waveforms, a lot of sophisticated waveforms. But the one common theme in most of those waveforms is that they're not really geared toward high bandwidth or data movement. A lot of it was based on being able to do command and control back when command and control was really done via voice, a commander giving commands to a warfighter. What's happening these days is a lot of what's needed on the battlefield is moving data around. And so in particular, when we see the introduction of AI, this is really amplifying that problem. So as the battlefield sensing, ISR, all this other information has to come back, it's got to be moved very quickly into AI processing. And to do that, you need a broadband data fabric. And it turns out a cellular network is very, very good at providing broadband data connections to a large number of devices. Another key aspect is what we call dual use technology. So increasingly MODs and Department of War are looking to leverage industry and take advantage of technology that's being developed and paid for commercial use and leverage that into defense specific applications and missions. And so this is a great example. 4G, 5G, 6G technology, huge investment coming from the industry, mobile network operators around the world, companies like Nokia, Ericsson, Samsung, and others to develop this technology. And so it just makes sense to figure out how can we apply it into defense use cases rather than having to create that new technology each time. Another key factor is a device ecosystem. So as we move into the world of AI, more and more sensors are going to be desired to go in various locations to gather data to feed those AI engines. To get those sensors connected, you need modems, you need devices, you need them to be low cost. And that's been proven out. We now have LTE in particular, huge volumes of very low cost devices that can connect into an LTE network. 5G is now coming on pretty strong. There's some new technologies that will enable lower costs, things like RedCap. But having that device ecosystem means that it becomes much easier to get sensors connected, and I can get a lot of devices onto the network in addition to the smartphones and the handheld devices that a human may carry. And then the final factor is commercial waveforms. And I touch on this one in the context of deploying this technology in a tactical environment or in a contested environment. What's happened over the last couple of decades is we've kind of transitioned from fighting fights with terrorists that maybe don't have super sophisticated EW systems to now thinking about Russia and others that do have very sophisticated EW systems. And so what that translates into is when you show up with a military waveform, that can be detected and it's immediately identified as a military waveform. If we can somehow leverage commercial technologies, that's going to blend in a little bit better into what all the other things that are happening in that particular location. Makes it harder to really identify, is that a target or not? And so to summarize this, why cellular? The big reason is huge investment by industry to develop a very advanced technology capability. And we want to figure out how we can leverage that for Department of War and MOD use cases. Now, the Department of War has really two key teams that have been focused on how to leverage cellular technology. There's the DoD, Department of War, CIO, 5G cross-functional team, which has defined, well, the Department of War CIO office, which really this is being run by the 5G cross-functional team led by Juan Ramirez, has defined 3 lines of effort. And these lines of effort are geared toward transitioning from kind of experiments with 5G to getting 5G rolled out for specific use cases. The first one is commercial 5G being deployed at installations. So this is basically making sure that commercial networks have good coverage across the base. Might sound fairly trivial, but very often those commercial network operators don't have access to the bases, and so they try to get coverage from the outside in. So this initiative is really to figure out how to get those MNOs physically on base so that they can deploy radios and base stations and whatnot on the base to get coverage. Second line of effort is then look at what are unique Department of War 5G features and systems. So what can I do with a private network context or a network slice or some other way to set up a 5G network that's targeting Department of War specific use cases. Sometimes we refer to these as operational use cases. And then the third is looking at expeditory and tactical. This is deploying, in a contested environment, downrange, where you need different types of systems. And this is happening today as well. There's another group in the Department of War, which is the Office of the Undersecretary of Defense, Research and Engineering, FutureG team. This is led by Dr. Tom Rondeau, who I believe was scheduled to be here, but unfortunately couldn't make it due to the government shutdown. That team, led by Dr. Rondeau, has defined a set of priorities. The first being resilient and open commercial solutions. So they really want to see openness so that they can ensure that as this technology is deployed by different military branches, by different militaries that want to work as coalition partners, that we have open standards we can interoperate and we know they're going to be available. It also is a big focus on open source. So Dr. Rondeau is really pushing for open source, providing funding to get Okudu as an example, which is Open CUDU, off the ground. That's another key area. Expeditory and tactical use. This is, as I mentioned a couple of times, deploying this technology in a contested environment for warfighters, looking at different ways we can do that. This is happening today with 4G and 5G. 6G will only make it better with the emphasis on AI. Ubiquitous, secure, and instant access. So really being able to connect anything. So making sure that whatever devices we have an easy and clean way to get them connected into the network. And then a big one that's coming up is integrated sensing and communication. I've got a few slides on this. This is a critical capability that can be used to provide another layer. If you think of sensor fusion, where you're going to have your exquisite radars, you may have video surveillance. This is enabling a 5G or 6G network to basically become a type of radar. And we'll talk more about what that's all about. And then agile spectrum operations. So spectrum sharing is going to become more and more critical, particularly as we try to open up new bands for 6G. And so we have to figure out how can we be very agile. The techniques that are developed for things like CBRS, relatively static. We want to make that much more agile so that we can have better use of the spectrum. So just a quick few bullets on where and how 5G is being deployed by the Department of War. So for going along those lines of effort that's defined by the 5G cross-functional team. So the first is just getting commercial 5G deployed. This is happening. It's not happening everywhere on every single base, but it is starting to pick up. And again, the idea here is to just get coverage on those installations. Some of them can be very large. Some of them, it's very, very difficult to get full coverage. You need to look at things like cell on wheels to get temporary coverage during activities and things like that. And this is also an important factor for what's called morale, welfare, and recreation. You have families that live on base. You want to make sure that they can buy a cellular plan and get good coverage for the things that they want to do in their daily lives. So for the more operational networks, these are some of the use cases that we're seeing. So training range deployments, being able to monitor training exercises across very large areas. It's very useful if you have a good 5G network. Covering the flight line for telemetry, for vehicle and equipment maintenance on the flight line. Logistics and warehouse automation, some very large logistics facilities. They're tough to cover with Wi-Fi, so 5G plays a role. And then getting good coverage across ships and on the pier side as those ships come into the pier. And then there's line of effort 3, tactical. So this is really critical to bring that data fabric for real-time distribution and increasingly focused on AI. As we see more AI, we see more data. As you see more data, you've got to have a fabric that's able to transport that data. And then as we deploy more sensors, various use cases, collecting sensor data, SATCOM distribution, coalition comms, things like that, where 5G is very, very useful. So coalition comms is an example. You can imagine NATO forces working together. What everybody has available is cell phones. And so if we can figure out how to make those cell phones work together, you've now got a common radio technology that's available across the various MODs that can be used for a coalition force. So looking forward to 6G, we've been thinking about this, and my colleagues in Nokia have been thinking about this obviously for quite some time. And I think this chart does a pretty good job of capturing what 6G is really shaping up to be all about. If you think back to 2G and 3G, really this was to enable human communications, largely voice communications, a little bit of data, mainly text messaging. 3G and 2G did a pretty good job of text messaging. But mostly it was connecting humans. There weren't a lot of devices being connected into these networks. When we get to 4G and 5G, we start to expand and we start to really think about connecting not only humans, but devices, and not so much focused on basic comms for humans, but now focused on data transport. And so we start to integrate into the picture more and more machines, IoT devices, vehicles, infrastructure that's all going to connect into those networks. When we think about 6G, yes, it will continue what we've done with 4G and 5G. And I'll talk a bit more about some of the key areas that I think about enhancements for 6G. But if you think about really what it's going to be all about at the end of the day, we think it's going to be all about AI. As we see more and more AI being deployed, what you're going to see is AI agents that are now going to not only be running in huge data centers, but distributed out into the network at various locations to execute tasks. We all already have these agents. They're sitting on most of our smartphones. If you've got a modern smartphone, it's got AI capabilities built in. That trend is going to continue. And so taking that 4G, 5G theme of having to have a data fabric that can move information between machines, this is only going to amplify with AI. Because now not only moving the data between machines, in the past where we'd be focused on getting it back to some data center, that data is now going to be delivered directly to AI agents so they can quickly provide intelligence and make sense of that information and potentially even act on that information over time. So another way to think about this is, the current networks that we're deploying are excellent at connecting people and devices, moving data around, doing this at very high speeds. with 5G, but really predominantly data transport systems. They're moving things usually back to a more central location for that data to be processed. In the future networks, they're going to evolve. And by the way, some of this evolution, I'll talk about this on another slide, is the use of AI to make those networks more efficient. So one of the things we talk about, or my colleagues in Nokia talk about, is a concept of AI for networks. And that the idea is, how can I use AI to build better networks? This slide is talking more about networks for AI. And so it's going to evolve from providing that connectivity to get data back to where, some data analytics or a human can analyze it, to ultimately embedding AI throughout the network, direct processing of AI tokens for an inference tasks in the network, in addition to transmitting data. So we're pretty excited about this. AI has a huge amount of promise, but the key thing I would say is that AI needs that fabric, and cellular technology is the ideal technology to provide that fabric in any situation where you're not inside a building or a large data center and you need to get that connectivity. Okay, so lots of stuff coming in 6G. This is really more of my view as I look at all of the developments that are coming in 6G. What are some of the key things in thinking about the Department of War and MODs and how this technology can be applied? And the first thing, of course, is opening up some new spectrum bands and introducing spectrum sharing. Those two kind of go hand in hand. It's a challenge to find new spectrum bands over time. There's incumbents. If we want to enable some of these bands, we're going to have to figure out a way to allow that spectrum to be shared with incumbents. In addition, we just want to get more efficient in the use of spectrum. So new spectrum bands, I'll talk a bit more about that on an upcoming slide. Energy efficiency. So this is very important. Depending on your outlook, the importance of it kind of shifts a little bit, and I'll talk a bit about this in another slide. If you're a large MNO operating a nationwide network, you think of energy as cost. What is it going to cost me to operate the network? How much does it cost me per bit that I'm transporting? The more it costs, the less profitable I'm going to be. But if you start thinking about this in a battlefield or tactical context, you start thinking about, well, energy's a valuable commodity that I have limited access to. If I'm battery operated in the far edge downrange, the more energy efficient these solutions are, the longer I can operate on whatever batteries I take with me. So energy efficiency is really critical. AI native RAN. This is another key capability, and I'll talk a bit about this on a couple of slides, but really leveraging AI technology to improve the RAN efficiency. I think there's some potential security aspects to this as well, and I'll hint on that when I get to that slide. And then finally, I already spent a bit of time talking about this one. Integrated sensing and communications. So embedding sensing into the network as an additional layer in a sensor fusion type deployment. Okay, so adding new spectrum bands. So one of the key bands that I know Bell Labs has been doing a lot of research looking at is this kind of 6.4 to 8.4 gigahertz band. It's about twice the frequency of the current midband where we've been deploying 5G. And what's interesting is if you think about these massive MIMO antennas, today we have antennas with on the order of 192 active transmitting antennas in it, or I should say panels with up to 192 antennas in it. In that same space, at those higher frequencies, we can get 4 times the number of transmitters. And with the 4 times the number of transmitters, that yields an extra 6 dBi of gain. And so we can get higher gain on these, which ultimately is going to ultimately is going to enable more capacity as well as more beams for beamforming and that sort of stuff. And so with this new band opening up, we think that we can, in the same volume of current radios, basically deliver very similar performance in terms of range, but do that at much higher capacity with much more capability. Now, there is one challenge, and this will hit back to the dynamic spectrum sharing that I mentioned. In the US government's big, beautiful bill that came out in the summer, there was some discussion of spectrum and spectrum sharing in that document. And there were certain bands that are controlled currently by the US government. One of them is it's roughly the 7 to 8 gigahertz band. And that was deemed off limits for commercial auctioning. So only a small slice of that band is becoming available. The rest of it is considered off limits. And I think that was based on a study that was conducted to look at the incumbent use and what it would cost to evacuate. So I think to get that band enabled and to enable these capabilities, we're going to have to solve the spectrum sharing problem. We've been quite active in that, in those efforts in Nokia Federal Solutions, as well as Nokia. We've done work with the US government on some 5G experiments, doing spectrum sharing a few years ago. We're just about to conduct an additional demonstration on spectrum sharing where we've expanded those capabilities, and that was all publicly announced by the government. So energy efficiency, this is a key capability for any MNO, and there's a bunch of things. I'll talk a bit more about them on the next slide. Some capabilities that day one 6G will provide, but really the goal here is to introduce significantly more capacity while simultaneously reducing energy. This is a non-trivial task. Fortunately, there's a bunch of really smart people across the globe that are looking into these problems in 3GPP. And I think there is a good shot at achieving some of these super ambitious goals. So if we just look at RAN energy saving on day one, so what are the kind of techniques? And if you look at the key targets over here on the right, they're kind of in two different buckets. One is, hey, how can we disable things when the network is at zero load? And so there's techniques to basically being able to shut down certain cells or certain beams in order to save energy. Also looking at signaling, how can we reduce the amount of signaling that's required so that you don't have to have as much energy dedicated to signaling. And so really the goal here is to get to near zero energy consumption at zero load. So if there's nobody active in the network, you can get to near zero load. It's non-trivial because you never know when somebody wants to fire up their device and get connected. So you have to figure out how to solve that problem. And then the other area is maximizing the bits per watt without compromising the quality of service or quality of experience that the user is going to get. And this one, to me, is very critical in a tactical network context because we're operating off battery power or off vehicle power. There's limited amount of power available. And so any techniques that we can use, one of those is looking at discontinuous transmission and reception, basically to enable less energy to be transmitted if you don't need the capacity at a given time. And then looking at different ways to adapt how those transmit antennas are being used in order to improve energy efficiency. I'm not an expert in all these techniques, but I'm pretty excited to see this work being done. And as I said, I think it applies both to the large scale MNOs as well as to Department of War and MOD use cases where battery usage and energy efficiency are going to be critical, or are critical and will continue to be critical. The next key area is AI native. This is very exciting. Nokia is leaning in pretty hard here. Nokia announced a couple of weeks ago a partnership with NVIDIA, focused on AI native RAN. This comes in multiple forms, and so this slide is really looking at what we would call as AI for networks. So how do we utilize AI inside the network and inside the network devices in order to make them more efficient? In the middle box here at the bottom is one of the areas that I know Bell Labs has done a lot of research in. DeepRX TX AI-based transmitter and receiver. The basic idea here, from my understanding, is using AI learning based on your channel conditions to adapt the constellation, the transmit constellation encoding scheme that's more optimal for those channel conditions. You're probably used to seeing a 256 QAM, nice 8x8 square that represents the code points. That's now changing. With AI, we've run these models, we run learning, and we discover that, hey, that's not the most optimal configuration. We've done this on different channel conditions. We've done it in generalized ways. And really, we're trying to refine, okay, how does this going to work? But the end result that we've been seeing is 1.5 to 2 dB improvement, which is pretty significant. And that's going to yield better spectral utilization, better range. So this really is a really good capability. I'm also excited about it in another way, which is for security purposes. Today the modulation coding schemes are well known. So if you're an adversary, you want to look at a signal, you kind of know what to expect and you can decode that signal. Obviously, we can encrypt things and do other things to protect the data. But I think by utilizing AI, if you can't get access to the models, it's going to be increasingly difficult to decode those signals. So I think we kind of get a natural encoding advantage in terms of security when we start applying AI. And then the other key area is looking at how do we apply AI for network automation. And so leveraging large language models to automate tasks. This will be agentic AI looking at various workflows required to operate a network, ultimately handing over some of those workflows to AI agents that are optimized and focused on those very specific things. So make the network easier to operate it, make it more efficient by leveraging AI technology. Another key area is network as a sensor, which is integrated sensing and communication. And so basic idea here is we're transmitting energy and waveforms on those 5G or future 6G radios. Those are going to reflect off of objects. So today we can, of course, locate objects by triangulating their transmission signals, but this will allow us to locate objects that aren't wirelessly transmitting at all. So this could be a number of different things. I'll talk about a few of the use cases on the next slide. The way I think of this is not as a replacement to the exquisite radars that are used, because this is going to have limited power. Obviously you can't do the same things you can do with the radar. It's not going to have the same resolution necessarily, but as a layer in a sensor fusion network, it can provide maybe capabilities looking in places where those exquisite radars aren't looking, or maybe becomes a first line of defense. And then you start firing up additional sensing to really zero in on what that object is and whether it represents a threat or not. Also would have commercial use cases for tracking various things. We'll talk about that in the next slide. So this is a diagram of a prototype that's been developed by Bell Labs. This is actually set up in Stuttgart, Germany. This initial prototype utilizes two radios. So there's a transmit radio that's actually running the normal 5G communications. And then there's a separate receive radio that's looking at the reflections. And the basic idea here is we can compare the transmit and receive signals, remove clutter, do some other things, and then ultimately build a pictogram that represents the reflections and where objects might be located in that reflected, based on that reflected signal. So some of the use cases that Bell Labs is looking at right now is looking at safety in context of factories and other enterprise settings. So you may have robots moving around where humans are also located. This could provide an early warning if a robot's about to come around a corner and run into a human, things like that. Roadway monitoring, so tracking vehicles across a roadway with reasonable resolution. You need to get down to 1 to 5 meters. And then the one that I think has the most interest, certainly I know from Department of War, this is of high interest today, which is drone tracking and intrusion detection. And so a lot of these drones are going to be coming, if you're conducting an attack, you're trying to do some type of covert surveillance, they're going to be flying at fairly low altitudes. Normal radars may not actually see them at those altitudes. However, if I've got a 5G network, it's largely going to be looking toward the ground. It's looking at the low altitude space, and it can see the drones. We've actually demonstrated at that Stuttgart facility at Bell Labs that we can in fact detect a drone. It's a pretty cool demonstration. You actually can see the drone on the pictogram way before the video feed is able to see the drone. So in summary, first and most key thing that I'd like to have as a takeaway is that cellular technology is really critical and is playing an important role for a number of different defense applications. So that includes deploying across permanent installations, bases, other kind of government facilities, and increasingly in tactical deployment. So rolling out with troops, enabling another layer of communications that can enhance and augment the existing military tactical radios that they have, and ultimately will become the key network fabric for AI. And so as we continue to enhance and use more AI, that's going to require much more data to be transported to enable AI processing. Cellular technology, 4G, 5G, 6G is going to be critical to enable that. And by the way, I include 4G here because the device ecosystem is so rich that it's got to be part of the equation. Over time, that may change, but right now, it's just the lowest cost, easiest way to get things connected, and it has pretty incredible capabilities if you compare it to traditional tactical waveforms. And then upcoming advancements in 6G are going to make things even better. So AI native RAN is going to improve the network. It's going to enable agentic AI to be deployed and distributed throughout the network. Spectrum sharing is going to become more and more critical. We've got to get better at how we use the spectrum. We've got to make that very dynamic. We have to have a nice balance between commercial and Department of War and MOD use. And then integrated sensing and communication is another key capability that's going to provide another layer of protection throughout 5G networks. I think initially starting in critical infrastructure, on military bases, around critical facilities, maybe sporting venues, borders, things like that. But eventually, I think this will get deployed across MNO networks once we figure out how to solve the cost equation. And so with all of that, pretty excited about the technology and what it can be done to improve performance, efficiency, and resiliency for a wide variety of use cases. Thanks a lot. I wish I could have been there. I hope you found the talk useful, and hopefully next year I'll be able to make it over there for the event.
Okay, thank you, Steve. Excellent presentation. So virtual thanks at least. So we have now chances to have some discussion. So anyone with Nokia who feels like being able to possibly respond, maybe you can come over here and then we can maybe have, if there are questions. So please. Yeah, that's good. And we have more Nokia people, so everyone is welcome who feels that they can answer. Okay, do we have questions? Yeah. Okay, so, yes.
Morning, I'm from Keysight, so I'm going to ask a test and measurement question. Your colleague was talking about AI RAN, and I put it in my mind because he spoke about the Department of War and Tactical Communications, AI RAN in that context. And my question is, how would you ensure that you have well-trained AI RAN network that can be deployed in an area where people are between life and death? How do we ensure that we get enough data to train those algorithms for those specific environments? It's just a question that's popped up in my mind when I saw the slides.
So I can start and then...
Sure.
That's an excellent question. So basically, I think that's a valid question when it comes to AI in general. So generalizability has been always the concern. Even with ChatGPT, you see that it's like all the time hallucinating when it comes to something that is not never seen before. So I think that the concern is very valid when it comes to, for example, DeepRX and DeepTX. And there are some countermeasures that we are taking, at least I'm aware that the colleagues are taking. So one of them is simply training on different environments where we have different channel conditions like line of sight, non-line of sight. There are a lot of like clutters and stuff. The other one could be like digital twin that we are also taking into account, that we are trying to, like for the cases that it's sort of like hard to do field measurements, then we can use like simulation environments thanks to NVIDIA and like our own sort of like simulators like Sampo that we have. We can have like pretty accurate sort of simulations environment where we can take the measurements and then train the AI on those. But long story short, I think there is no definitive answer to that question, because it's always been the field of research to have generalizable models when it comes to AI. So if you have anything else.
Yeah, I mean, just to add that when we talk about AI RAN, we are not discounting the fact that the traditional algorithms and the traditional logic about deciding does it work, does it not work, still holds. So when you do AI RAN, it doesn't mean you throw away everything else that is there. So thinking about that, I mean, if we think about Ukraine, we don't have a lot of realistic models, but then at least the wireless community has explored enough and has seen enough scenarios that we can make a good judgment as to like what works and what doesn't work and what we need to train on and what degree of confidence do we have over the output of our models. So, you know, in Nokia, we always keep that in mind that, you know, whenever we have a certain result, we are looking at the degree of confidence with which we can say it works and degree of confidence with which we can say that there is a good chance that it might not work. And that is something that we need to keep in mind. So nothing is foolproof, basically.
Yeah, Paul van der Wiel from TNO in The Hague in the Netherlands. Thank you. Yeah, on the topic of detecting drones using networks, right? Is it possible to share anything on how far you have come on existing commercial hardware, like the mid-band massive MIMO antennas, which are out there now? And maybe not the software, right? But the hardware, what you could achieve in terms of accuracy and how far inter-site distance, things like that, you could detect drones, for example.
Yeah, so maybe I can just give a very rough answer that, you know, the accuracy within which you can detect a drone was within a few meters of like the actual position. I mean, the exact numbers will depend. The reason I say within a few meters is because the exact number really depends on the scenario that you're in. So if you have a lot of high-rise buildings, that degree of accuracy will degrade for sure. So, but yeah, I think the demo that we saw was with a commercial FR1 radio, and I think it was still with 192 antenna elements, but then, of course, the algorithms that the researchers are exploring, I think we ourselves are exploring, they should be generalizable to different scenarios, and that is the objective and goal for that. So yeah, it's a mix of having the right hardware and the right algorithms and what works and what we see into the future as different scenarios.
A quick one. My question is about AI. I think coming from telecommunication research background, I can see that AI is now driving the discussion in moving some technology pieces from telco to cloud. And now with resilience, we have also this AI on the table. And I believe as telco researchers and industry, you have to be very clear on what are we demanding for the AI experts, which is another community where we have, of course, intersection. So my question here is, do you think that here we're speaking about about Gen AI, where we can automatically, for example, create a configuration, because here it's about automation of configuration for network. So if there is a new need of resources in the network, then you have some sort of tool like Gen AI. You prompt a question automatically, and then you have the configuration. Equipments are configured. Or we are speaking about this augmented intelligence, because the telco equipments already, had intelligence, like with admission control, with scheduling. It's just that we use now new learning and new AI tools to augment this intelligence. But intelligence was already there. It wasn't the same methods. So for me, the question for the industry is, on the short term, mid-term, and long term, what are we expecting, demanding to the AI developments? Thank you.
Yeah. So, yeah, I mean, should I answer the question? Yeah. Yeah, so just to answer your question, I think it's a very important question, right? I mean, we are now thinking about AI, there is NVIDIA, and there's this huge hype going around. So let's think about it in a much more pragmatic sense. I mean, and I think my colleagues from Bolden Networks will sort of agree that configuring private networks is not some of the easiest job. Like 4 years ago, I was doing it in the field in Spain, and it takes a long time to even get the network correctly configured. So I think intent-driven networking, deployment, optimization of the various parameters is a fair game for, AI and AI-driven, network optimization and configuration, because it's really hard in principle. And if you give it to the IT/OT teams of, let's say, an industry, they don't know anything about telco networks like operators, researchers, and the industry understands it. So yeah, short term, I think we are already addressing some of the important problems, which is like network performance optimization. And then medium term is something that we saw on the slides, right? I mean, the DeepTX, DeepRX, collaboration with Qualcomm, and now with NVIDIA coming in with the expectation of like, you know, something on the edge. These are things that I think are, that I would believe are midterm. And then long term goes a bit more like, you know, agentic AI and how do we want to interpret that? Because the word agentic is nice and cool. It's great when nobody's life is on the line or criticality is not on the line, but then, you know, when things start to become critical, that's when you need guardrails. And the AI research community itself has not been able to set the correct guardrails. I mean, if you think about the discussion, and I don't know if some of you are going to go to this ELIS AI summit that is going to happen in Oulu or Turku in a few weeks, where they're going to talk about the AI Act and, you know, the guardrails on AI and the AI research in general. I think we need to look to that community to see like how do they rein in the capacity of AI and what it can do, because we are dealing with something that affects millions of lives even though we take it for granted. It's like how we take electricity for granted, like we take networks for granted, but it takes a lot of effort to keep them up and running reliably. So we need to be careful with where we go, and that takes time. So I don't know if you have something.
Yeah, and I would say in the short term, I think troubleshooting is also another aspect that generative AI can play a really important role, because I mean quite often the troubleshooting, I mean we had some field tests with Akshay before, like I mean a few weeks ago. In troubleshooting what is wrong and what is happening there that is not as you were expecting, that's something that I think based on the documentation it should be clear, but when it comes to like really doing the job as an engineer, that's a very complicated thing, and I think that's something that generative AI can also help, like by reading the documentation and stuff and providing some help, I would say.
And just wait for our paper.
We had two more questions, so let's make them quickly, and one reply only, so I think we are running out of time, so let's take them quickly and then.
Yep. Hello, my name is Natalie Åström Alves-Pinto. I'm from the European Space Agency. Greetings from Oxford, United Kingdom. I'm Finnish myself, but I live in the UK. I work for the 5G, 6G, NTN office at the European Space Agency. I was surprised to not see satellite and or NTN / convergence between terrestrial and satellite networks referenced much in the presentation from Nokia.
Yep.
From ESA side, as an intergovernmental organization with 23 member states, our perspective is that satellite is a complement to terrestrial communication. So I would be curious to hear your perspective on that.
Yeah,
Yes, thank you.
Long story short, it is an important aspect, and Nokia driving also Nokia being an integral part of 3GPP and 3GPP looking at NT-NTN blend in. We fully believe and are fully on board with that aspect. I think the presentation was trying to highlight some of the other aspects, because I think NTN and TN is somewhat like, you know, starting to mature in terms of standards, and then there is also a lot of public information out there, like how Nokia is working with different stakeholders in terms of like NTN, TN integration. So it's not that we're taking it off the books. So yeah.
You hear me? Yeah. This is Frank Röger from Rohde & Schwarz. I have one question that came to my mind, because I've seen it at several times on your slides, is about tactical networks. So as we all know that technical radios are designed to hide from the enemy, use frequency hopping, things like this, not to be located, not to be spoofed by the enemy. And if you look about cellular networks, they are not at all designed for this purpose. Yes. So how do you came to this conclusion for this application?
Great question. I will refer one small paper that we published in the NATO ICMCIS conference that year, where we tried to address exactly this problem. So 5G, 6G networks or cellular networks, when they were designed, they were not designed for tactical purposes. I mean, they were designed for connectivity, as Steve also said. It came from connectivity, then data, transmitting data, and now we are starting to think that how could we leverage them in the tactical scenarios. So yes, there are a lot of things that need to be done if we want to hide them in plain sight, as you're referring to. And there are a few things like spectrum sharing. You know, if you think about it a bit more, spectrum sharing can mean, you know, and he also referenced to the point that, yeah, like military waveforms are easily identifiable because the adversary knows you're going to use these kind of waveforms, and they have built their own classification methods to like detect and analyze. And if you're using specific bands, then that's also a big giveaway. But then, you know, commercial 5G networks, they work in a specific band, but if you blend in through spectrum sharing, then you can sort of create this illusion that you are a normal network, but you're not. So there are these kind of things that, you know, you can play around with that the standard allows without breaking the economies of scale that we are actually looking to leverage for tactical networks. So yeah, we need to think about all these levers and nuts and bolts that we need to get this to work together without destroying the economies of scale, of course. So yeah.
Okay, let's thank the speakers.